So what do we have? We have the modulation functions. Remember this from a couple classes ago. Modulation functions Si of k are equal to alpha I times some basis vector S of k. We defined, so let's let S be the equivalent, S vector be the equivalent vector to S of k. And we defined norm of S equal to 1. That's one of the things that I said a couple of classes ago. So this is just a definition. This is a way to set up the problem. I did that for convenience, and we're about to see why that's convenient. So what do we have? We have the noise-free filter outputs Si is equal to Si vector dot H hat vector, which is equal to alpha I times S vector dot H vector. So we have, you can think of these as vectors. So now Si vector is equal to alpha I times S vector, where S is the basis vector. So geometrically, what does that look like? Here's the geometrical interpretation of what's going on. So here's S, let's say. So here's the origin. Here's my basis vector S. And it's in this direction that all my signals lie. And remember, leading up to this, we have the assumption that they're all equally spaced and blah, blah, blah. Okay, so for instance, S0, S1, S2, and so on and so on and so on. What am I doing? I'm taking the dot product between Si and H. Si is parallel to S by definition. All I'm doing with S is I'm scaling it. So all the Si's are parallel to S. H is not necessarily parallel to S. So let's let this be the H direction. When I take the dot product with a unit norm vector, that's equivalent to projecting, or with the unit norm vector H hat vector, that's equivalent to projecting the vector onto the H hat axis. So remember, from a long time ago, you should remember that A dot B is equal to norm A, norm B times the cosine of the angle between them. Let's say B is unit norm in that case. Then we have A cos theta, which is just the projection of A in the B direction. So now we're projecting things in the H hat direction. So now we have this. So it's perhaps not easy to see, but this distance should be shorter than that one. In fact, it's probably more dramatic if I do something like this. Let's say H hat is in this direction down here. And the projections are like this. And so on. So geometrically, this is D. If H hat is in this direction, then this is D. Because remember, or oh, excuse me, these are not S0, these are alpha. Alpha 0, alpha 1, alpha 2. The S's are what happens after I pass it through the filter, so that would be these. S0, S1, S2. Or with this inner product with this vector, here's what I have, S0, S1, S2. And then these like this. So what I want to do is I want to maximize D. Which is to say I want to maximize the inner product S dot H hat. So given this geometric interpretation, what's the way in which to maximize D? What's the way in which to maximize the dot product?
Take H parallel to the basis vector.
Exactly. If I swing H so that it's parallel to the basis vector, if it's not parallel with the basis vector, then the gap between adjacent points shrinks because, well, basically, if you look here, it's because cosine of theta is always less than 1. So as I swing this around and it becomes closer and closer to, let's say, 90 degrees, this gap will shrink to 0. If I want this gap to be maximum, then I need H to be, so H hat has to be parallel with S. And that's in fact exactly this same interpretation can be applied to the binary case. The only difference is that in the binary case we have only 2 vectors, and in this case we have multiple. So in fact, this here is a geometric interpretation of the Cauchy-Schwarz inequality. Remember the Cauchy-Schwarz inequality, which is what the tool we use to prove that this vector, that H was the matched filter. This is a geometric interpretation of the Cauchy-Schwarz. So the lesson is H hat, well, it has to be parallel with S, but what we said was that, so basically that means H hat has to be alpha times S, the basis vector. But what we said was that, or what we required was that H hat had unit norm. So basically we have to pick alpha so that this has unit norm, but S hat already has unit norm. So therefore we can select H hat equals S. So my matched filter, this is the key takeaway lesson here. The matched filter there's a one-to-one relationship between the matched filter and the basis vector for the signal space. Secondly, what are my noise-free matched filter outputs now? Si is equal to Si vector dot H hat vector, which is Si vector dot S vector, and where S is the basis function, the basis signal in the signal space, and Si is equal to alpha I times that same basis dot S. If I dot S with itself, what do I get?